So for this part, we're going to talk about turning points of polynomial functions. So turning points basically means when a function graph changes directions. So we've seen it before in increasing and decreasing behavior. So we see that when it changes from increasing to decreasing, it changes slope, changes direction. So one example is, for example, right here, if I were to look from left to right for x to the fourth, we see that it's decreasing and then it changed to increasing. So basically we've seen it before, it's just we never talk about the points that it turns. So let's take a look at x to the fourth. We see that there's a turning point right here, another one right there, and then a last one right there. So the turning point is when they changes slope, changes directions, or to tie into increasing and decreasing, it changed from decreasing to increasing, and then from increasing to decreasing again, and now the last one, decreasing to increasing. So it changes 3 times here. Let's take a look at x to the third. So we see that the turning point, and again, you don't have to look from left to right or right to left, doesn't really matter. It's just as long as you can tell where it changes direction. So let's take a look. We see one change right here and then another one right there. So there's 2 changes, 2 turning points for x to the third. Let's take a look at x to the fifth. So say I start from the left side. So right here, there's one turning point. Here's a second one. And then here's a third one. And then lastly, a fourth one. So for the graph of x to the fifth, there's 4 turning points. Seems like there might be a pattern. So let's take a look at negative x to the sixth. So again, we're just looking at the turning points where it changes from increasing to decreasing or decreasing to increasing, or just basically changes slope. So let's take a look. We see we have one right here. We have our second one right there. Then here's our third one. Here is our fourth. And then here is our fifth. So for negative x to the sixth, we have 5 turning points. So I mentioned before that there's a pattern. So let's take a look. For x to the fourth exponent, there's 3 turning points. For x to the third exponent, there's 2 turning points. And then x to the fifth exponent, there's 4 turning points. And then negative x to the sixth power, so the sixth exponent, there's 5 turning points. So it seems that whatever exponents there are in these examples, there seems to be one less of the turning points. So what I mean by one less, let's take a look at this one right here. If it's x to the fourth power, that means one less, which is 3, so there should be 3 turning points. Let's look at x to the third. Since it's to the third power, so one less is 2, so it should be 2 turning points. X to the fifth, one less would be 4, so there should be 4 turning points. And then negative x to the sixth, so one less would be 5. So 1, 2, 3, 4, 5 turning points. So the pattern here for turning points would be exponent. So let's write out the rule. So x to the n power. So n represents the exponent. So turning points. Now I'm going to label turning points of polynomial function, but I'm just going to write turning points. Usually, and I use the keyword usually, equals to n minus 1. So most time when you have x to the n power, where n is the leading degree, so let me write out, or let me specify that n is the leading degree. So n is the leading degree. So your highest exponent. So when you are trying to determine turning points, when you have x to the n where n is the leading degree, usually or most cases your turning points would be n minus 1. So for example, if n was 7, 7 minus 1 is 6, so you should have 6 turning points most of the time. There are special cases where on a graph it looks less, but most of the time this is what you will follow for the rule. Alright, let's go over some examples with turning points. So we have two examples. F of x equals 2x plus 4x squared minus x to the fourth minus 1. And then g of x equals negative 4x to the third plus 2x minus 6x to the fifth plus 3. So based on this information written here, what you're going to do is we're going to focus on f of x first. So again, what we're going to do is look for the leading degree. So we have 1, 2, and 4. So our highest leading degree is 4. So I'm going to write that. So now when we're determining turning points, we're going to do n minus 1. So if I were to show you step by step, 4 minus 1, which is 3. So basically, that's a 3, sorry. So following this principle, this rule or concept, there should be 3 turning points. For that example. Now moving on to example 2, our leading degree, let me write it down here. So let's take a look. G of x equals negative 4x to the third plus 2x minus 6x to the fifth plus 3. So our exponents is 3, invisible 1, and 5. So out of those 3, our highest is 5. So we're going to write 5 here. Now following this rule, turning points, I'm going to do 5 minus 1, which is 4. So this function, the graph, should have 4 turning points. So basically that's all you have to do when it comes to identifying turning points. Look for the leading degree and then subtract 1, and then that should be your turning point in terms of what the graph would look like, but not all the time, would look like. So f of x has 3 turning points, g of x had 4 turning points. And again, to review, this rule usually works most of the time, depending on what zeros you have. So again, turning points, usually it's n minus 1. So if it's 4, if your leading degree is 4, 3 turning points. If your leading degree is 5, 4 turning points.